Now we're going to look at the first of our T procedures, the one sample t-test. You might notice that I have one sample in parentheses here. Most of the time people don't even say one sample, they just say t-test. It's that common. The purpose of this test is to test the null hypothesis that a population mean mu is equal to some particular value mu naught. The conditions are simple random sample and normal population. Now you might notice that when you're working with the sampling distribution for x bar, there will be a third condition, that the population is greater than or equal to 10 times the sample size. Most of the time when you're using these T procedures, that condition is so obviously met that people don't even bother checking it. But you should always think about whether or not your sample observations are independent, and if you're faced with a large sample or a small population, always keep that in the back of your mind. That's something you want to look into in those circumstances. The formula is T equals x bar minus mu naught divided by S over the square root of n. This is a standardized test statistic. We have a sample statistic x bar, that's the sample mean, minus the hypothesized population mean divided by its standard error, S over the square root of n. So that has the same structure as a Z statistic, except here we have S instead of sigma. Calculator, stat test 2, t-test. And I'll say more about that when we get to that. Okay, let's look at an example. Jimbo, he loves to eat a certain kind of candy bar, which is nominally of 1 ounce weight, as stated on the package, but he suspects that the candy bars are actually lighter than that. So he buys 10 bars at random and weighs them, and he gets these 10 weights. So this is these are his sample data, the sample weights. And you notice that most of them are around 1. They're pretty close to 1. Some are lower, some are higher. Do these weights provide evidence that on average the bars weigh less than 1 ounce? Your null hypothesis would be that mu is equal to 1. The mean weight of this kind of 1 ounce candy bar is 1 ounce, versus the alternative that mu is less than 1. The mean weight of this kind of 1 ounce candy bar is less than 1 ounce. Now the conditions are just the two. Simple random sample. Can't say for sure that we have that. In all likelihood we don't, but we do have a random sample. It should be representative. Normal population. Well, we're not told that we have a normal population, so that's a problem. The first backup in that situation is the central limit theorem, where if your sample size is large enough, the sampling distribution of x bar is going to be approximately normal, even if the population is not. But in this case, we only have a sample size of 10, and we would typically need a sample size of 30 or 40 in order for the central limit theorem to work. So we don't have that backup. Our second backup is to actually look at the data. You want to make a graph of the data and then see if the graph is consistent with the normal population. Well, here is the stem plot that I made of the data, of the weights. They range from 0.95 ounces to 1.02 ounces. The distribution of the sample weights is symmetric, single-peaked, free of outliers, and so you could argue that these data come from a normal population without knowing for sure that they do. Okay, so that second condition is met based on how the data look. When you're looking at the data, the stem plot is usually the best, easiest way to graph the data if you are working with a small sample. You could use a modified box plot to see if there are any outliers. You could use a normal probability plot, and if the normal probability plot is relatively straight, then you could argue that the data come from a normal distribution. So there are other methods besides the stem plot that you can use. The t statistic again is x bar minus mu naught over S over the square root of n. I calculated using one variable stats that the mean x bar is 0.985 and the sample standard deviation is 0.022. We know that the sample size is 10. This statistic has 10 minus 1 or 9 degrees of freedom, and when you simplify it, it works out to be negative 2.183. You can find the p-value either using a table or the calculator. I'll show you how that's done in a minute. The probability that t is less than negative 2.183 is about 0.0284. That's less than 5%, so I would reject the null hypothesis based on that, and then my conclusion would be I reject the null hypothesis that the mean weight of this kind of 1 ounce candy bar is 1 ounce, and find evidence that the mean weight is less than 1 ounce. Now, if you want to do this test on the calculator, you have a couple of options. in order to make a graph of the data and find the sample mean and the standard deviation, you want to put your data into a list. So I put my data into list 1, and there they are. And then you can run one variable stats and get the summary statistics like X bar and S. And then when you have that, you could go and run the test. Go to stat tests and go to number 2, t-test. You have the option of running this test from the stats. If you choose that, it will put the sample mean in there for you. It will put the sample standard deviation in there for you and the sample size. You have to provide the null hypothesis value, and you have to provide the correct alternative. And then you can come down here and calculate, and this will give you your t-statistic, your p-value, and it'll repeat the other summary statistics that we just mentioned. So that's one way to do it from summary statistics. If you want to do it straight from the data, you also have that option. You can go to stat tests 2 and and then you can select to do this from the data. Now when you do that, you have to tell the calculator where the data are. I have them in list 1, and here's my null hypothesis value, here's my alternative, and you can come down here and calculate based on that, or you can draw a picture if you want, and that's always kind of nice. It takes a little longer, but gives you a nice picture which you can copy onto your paper when you're doing this on your exam. And there you go, you see your t-statistic and your p-value, and you get a nice picture of the t-distribution with 9 degrees of freedom, and your p-value shaded over there in the corner. Now if you do the work by hand, as we did up above, and you calculate the t-statistic to be negative 2.183, you can use normal, you can use TCDF, on the, go to second vars and go down here to number 6, and then you can put in the t-statistic and the boundary, and then it's left bound, right bound degrees of freedom. So since we're looking at a left tail here, we put in negative 999, then we would put in our negative 2.183 for our t-statistic, and then we would have 9 degrees of freedom, and we put that in, and then this will calculate the p-value for you. So that's another way you can do it. So you have options. The calculator is very powerful, and it can do a lot of these different things.